Chapter 9 begins representing curves in new ways or different formats. So that'll be parametric curves, and then polar coordinates will be the two topics that we focus on, and alternate representations of planar curves. So what we've done so far, generally for functions, is something along the lines of y equals f of x. So we've represented a curve as the points x and y that satisfy some equation, y equals f of x, or y equals some function of x. Uh, Parametric curves leave us some really nice options in terms of how we might work with these functions or curves, and how we might gather some information about them. They can really simplify calculations in some cases. This is really just an introduction to this. Calculus 3, or a course beyond this, will really take this much further, and you'll learn to do much more with parametric equations. That's very useful in physical or engineering settings. So to get started, we can express the coordinates of a curve in terms of functions of some parameter t. So where we used to deal with just y and x, related via y equals f of x, now we introduce a third variable t, which is more or less a third dimension we might think of. So if x and y were two dimensions, we now have this third parameter, this third degree of freedom, or this third dimension t. The way that the points in the plane will be represented is still x and y, but x is some function of t, f of t, and y is a function g of t. So these are distinct from each other. We can split it up and write it in this form: x equals f of t and y equals g of t. Sometimes, to take this a little bit shorter, we might write x as x of t, x as a function of t, and then the y coordinate as a function of t as well, y of t. So some of these notations will be used interchangeably. And lastly, we'll use c of t to represent a curve in the xy plane. So multiple different notations we're seeing right here, but this is all among the realm of parametric equations. So what used to be a function y equals f of x is now written as a single equation. We now technically have two equations representing a point on the curve. And let's see what sort of possibilities this opens up, how this changes two-dimensional curves as we understand them and work with them, just by introducing this new representation. So to introduce ourselves to these, this might be familiar territory. Students might have seen this before in a physics class, possibly an algebra class or a pre-calculus class. But they ask us to sketch the graph and describe the parametric curve c of t equals 2t minus 4 and 3 plus t squared. So we're given c of t, some planar curve as a function of t. It's got an x component and a y component, or an x function and a y function, we might say. And they ask us to graph the curve, so we just pick arbitrary values of t. I've chosen -2 through +2. And what we do is we plug in that t value for each of these functions of t to get first our x coordinate and then our y coordinate. And that's what this table is doing right here. The x and y values for each t value that we might plug in. So when we do so, we get -8, 7, -6, 4, -4, 3, -2, 4, and 0, 7. Those are all xy coordinates on this curve. We plot all 5 of those. Well, we plot 4 of the 5. One of them is off the screen here, off the graph here. So at t equals -1, we have -6, 4 here. And I don't label the point because we can see that on the axes. But I do like to label the time. It's a good idea to know when or where that occurs, for what parameter value that might occur. Notice I did just call t time. That's often how we think of this parameter t. We can think of it in the sense that we're at a position xy at time t equals -1. Now, negative time might not make sense, but just mathematically speaking, without using this in a physical setting, -t is just fine. Negative parameters are okay. So then t equals 0, we have the point -4, 3, once again, so we can recognize that all these points are in here. what happened here first was we plotted these points, and then we realized that, oh, this is sort of a U-shaped graph. And then we extrapolated and said, well, this is probably a parabola passing through these points. One hint about that would be to look here and here and realize we have a linear function of t and x, then a quadratic function of t and y, or a squared function of t. So there's a good chance that this thing looks like a parabola, or at least a section of a parabola. Now they don't specify the domain of t, so what we assume in this case then is that it's for all values on which these functions are defined. Both of those functions are defined on all values of t, so it's from negative infinity to infinity. So this curve does extend indefinitely to the left and up, and indefinitely to the right and up. So we just draw it as that. Now, let's confirm that this thing is actually quadratic. So if we were to just look at this curve as y equals f of x, ignoring t, so can we prove that that's a quadratic function? Well, the way to do that is called eliminating the parameter. And that's what we'll do below. If we want to know what a parametric curve is, if we're not able to tell just by inspection, we can attempt to eliminate the parameter t, rewrite the function as in a y equals f of x form, and then identify it from there from classical algebraic functions. So eliminating the parameter looks like this. We take our x function, which is the first component of c. You can see that up here. And then our y component is that second function. That's y equals 3 plus t squared. And we need to eliminate t. So in other words, solve for t on either one of these equations. It'll be easier to solve for t for the x equation because t is not squared. So we go with that and we discover that t is equal to x plus 4 over 2. That being the case, we plug in this t value to t squared for our y expression, and that effectively eliminates the parameter at this step right here. That's our 3 plus t squared step. So subbed in this x plus 4 over 2 for t. Now we have a function entirely in terms of y and x, or y equals a function of x. And then we can FOIL that out or multiply out the x plus 4 over 2 squared. And what we arrive at is a function y equals 1/4 quantity x plus 4 squared plus 3. That's the standard form of a parabola with vertex at -4, +3. Remember how to read the vertex off of this standard form. So -4, +3, and that's exactly where we had a vertex on this graph. So we noticed that t equals -1 and t equals +1, that we were sort of concave up along this, and that t equals 0, well, it just might be the vertex of that parabola. T equals 0 won't always be the vertex of these parabolas in parametric functions. We just got lucky in this case. But we confirm that down here with this equation, standard form of a parabola. So it is in fact quadratic, it is a parabola, and we did get the vertex right in the graph. You might do this eliminate the parameter method concurrently or simultaneously with attempting to graph the function. Or you might do this, you might graph it first, eliminate the parameter, find this equation, and then correct your graph up here. So these are sort of interchangeable processes. The next, a little bit more of a practical use for this. This is a common physics 1 type problem. So projectile has height and horizontal distance described by the parametric equations. X of t is equal to 200t, y of t is 400t minus 16t squared, and that projectile travels between times 0 to 25 for t. Okay, and they ask us to find the height of the projectile at time t equals 5, and then find the horizontal distance from its initial point, time t equals 0. So that's where it starts, is whatever its position is at t equals 0. And then we find how far it travels horizontally by the time it reaches its maximum height. Now remember what this means. Here's the flat ground. This trajectory is something like this. So how far has it gone from here to here once it's reached the apex of its height? So, or of its trajectory, we might say. For the first one, what's the height of the projectile at time t equals 5? That's very easy. Just plug in t equals 5. Y is telling us the height. We're plugging it into this function. We'll get a number out, and I'll let the student fill in the details there. Now the max height, what we want to find the distance, the horizontal distance when this projectile is at its maximum height. So we see the word maximum, so we think, okay, this is some optimization scenario. In calculus 1, what did we do for optimization? We took our given function, we took its derivative and set it equal to 0. It's exactly what we do here. We take y of t, we take the derivative of it and set it equal to 0. The derivative of this function is this. Setting it equal to 0 gives us that right-hand side. And we solve for t to get t equals 12.5. So now we know the time at which the maximum height occurs. So that was the first question. When does the maximum height occur? Okay, well, we've got that at 12.5. Now it's easy to determine what the horizontal distance is because the function x of t is telling us how far this thing travels horizontally. So x of t, we just plug in x of 12.5, and that's 200 times 12.5 to get 2,500. Is there a unit to this? Maybe it's just 2,500. They don't give us any units. So yeah, 2,500 units is what we'll say. It's a nice math problem. We don't care about the units. We just want to do the mathematical components of it. Okay, so that handles a really basic version of one of these trajectory problems, but it's probably a familiar place for most students. But we do have a little bit of calculus involved, and that's a nice thing to see and a nice tool to remember for these problems. So let's return to a more mathematical example, and this is to find the parameterization for a fairly well-known algebraic entity, and that's a line through a given point with a given slope. So we're asked to find a parameterization through this point of the line through this point with a slope m equals 4. So what they're asking for is a function c of t equals an x component, function x of t and a function y of t. So when I see a point and a slope, the first thing I think of is point-slope form, and that's this right here, where m is the slope, x naught, y naught is the point. So we plug in 4 for the slope as given, and then 3 and -1 for x naught and y naught into that form. When we simplify this, we arrive at a function y equals f of x, or 4x minus 13 in this case. Which is good, it's just not this parameterization that we're looking for. Now, the easiest thing we can do in one of these situations is to say, well, let's let x just be equal to t. X of t can be t, and if that's the case, then everywhere I see an x in this function, I'll replace it with a t, and that's pretty straightforward. So we have x of t equals t, and y of t equals 4t minus 13. To write that as a function c of t, we just append these two functions together with a comma in an ordered pair like this. And now we've got the collection of points in the plane, t comma 4t minus 13. One thing we should add to this is the domain, the values of t on which this is valid. Well, since it's a line going infinitely in either direction, we should go from -infinity to infinity. And to simplify things, we should probably, as long as the function is defined, or as long as we're capturing the section of this line or line segment that we're supposed to come up with, we should probably pick the most general domain we can. You want to be careful to make sure that you're only defining exactly the segment or the full length of the line or curve that you're trying to describe with this parametric notation. Okay, there's another solution for this, and this is what's interesting about one of the most interesting things about parametric equations is we have a lot of liberty in how we might represent any given function, y equals f of x. Really, there are infinitely many different parameterizations we can come up with for any given y equals f of x Cartesian curve. Okay, so a general way to come up with the equation of a line through a point x naught, y naught, with slope m equals delta y over delta x. So what I'm saying here is that m, the slope, can always be thought of as a ratio delta y over delta x. In our case, the slope is 4, and 4 is technically the fraction 4 over 1. So the rise over run and slope like that is 4 over 1. So let's just think about these things in terms of rise over run. And a general formula for finding the parametric equation for a line as asked in this equation or this example is to do the following. C of t is equal to x naught, the x coordinate of the point, plus delta x times t. T is going to be a variable. And similarly, it's y naught plus delta y times t, where t is still the same variable. And that'll give us a function of t in each of these components. Let's remember to note this as well. T will range from negative infinity to infinity, and this will capture the full length of a line, and particularly of this line that we're dealing with in this case. So here's x naught is 3, y naught is -1. The last step for delta x and delta y is to put in 1 times t and 4 times t, as we saw off to the right. And this will also be a parameterization of the same line from negative infinity to infinity, or t. So it's important enough that I'll add this domain to this answer. Things were boxed up quickly prior to completing this example. So, as we see, there are two different parameterizations. Both of these work. You might want to check t equals 0 on this line to see that we're actually at the point 3, -1, which is the point that we wanted to guarantee was on this curve. So that's what's kind of nice about this representation, because you can immediately check that the line's on there. It's maybe a little bit more difficult to check the slope, whereas this one might be a little bit easier to see because it's inherited directly from here. We have 4x minus 13, so we can see the slope a little bit better in this one versus the other one. Really though, all we have to notice in this one is what the coefficient of t is for y of t divided by the coefficient of t for x of t. That's 4/1, and we're going to get our slope from here as well. So two different parameterizations, same line. We could go on forever. There are infinitely many parameterizations for functions. A lot of things are sort of canonical, or the sort of the go-to parameterization for things. In the case of lines, this one is probably that canonical representation. So keep that in mind if you're looking for sort of the go-to parameterization for a line. Now we'll look at some further examples in the next video. So be sure to check that out. And good luck with the problems leading up to this point.